delivered by Professor Molchanov, our Russian fellow. Please.
I have these several lectures about localization theory. It means that we will study the spectral properties of the operator, which looks like classical Anderson model. There is Schrödinger operator on the lattice or in the A2 on the Euclidean space with random potential, and we want to prove that in some cases the spectrum of this operator is pure point, which means physically that in corresponding random medium it's impossible propagation of the waves, sound, light, and so on and so forth. It's amorphic media. Or maybe we have some kind of phase transition for some interval of energies we have localization, for others we have continuous spectrum, and so on and so forth. But I will concentrate on two particular models. First of all, it will be Sierpinski lattice. Sierpinski lattice is a well-known object, closely related to Sierpinski gasket. This is self-similar fractal. On this fractal, you can introduce good measure, very natural Laplace operator, fractal Brownian motion, and so on and so forth. But for this operator, I will prove localization theorem, at least under some class of the random potentials. And second object will be hierarchical Anderson model when we have very special phase space. It's so-called ultrametric space. Is a topic which was introduced by Bogolyubov's school in the theory of superconductivity, and for this, on this ultimate space, space is possible to define a Laplace operator. It will be in fact fractional power of some canonical operator, and in this sense, this topic will be close to the area of our conference. And I will prove some statistical general result about the relation of this. But I will start from, in some sense, toy model. It's one-dimensional model which will explain new approach to the spectral theory based on the physical intuition, based on not through the formal mathematical calculation, but on the physical interpretation of the phenomenon of localization. And I will discuss today, and maybe next lecture, if I will not finish today, the following. In particular, we have positive undirected lattices, and they will be one, and we have operator delta. It's standard lattice Laplace operator, psi x plus 1 plus psi x minus 1 minus psi of x. This operator, of course, can be considered as a generator of the symmetric random walk with continuous time on the lattice. But I will not work with this probabilistic random walk. Instead, I will introduce something which is possible to call that's Feynman type random walk. It's a quantum random walk. We have this operator and we have Hamiltonian H psi is delta psi plus V of x times psi. I will not assume that potential V of x is random. It's not 100%. It's pure deterministic. When many years ago we published the first papers about localization for one-dimensional random Schrödinger operator, it was continuous series. Later on, Kunz and Suyar in France developed lattice version, the same localization theorem. And when I gave talk about all this stuff on the similar way, well-known specialists, Levitan, Marchenko, Gelfand, it's people who solved inverse spectral problem. And Levitan says that you must show me a real example of localization. What does it mean random operator? And almost all. Can you find one particular realization of this operator for which we have point spectrum? That was I had no answer. But now I will present the following result. We have this operator. We have boundary condition. Psi to the point -1 times cosine theta naught plus psi at the point 0 sinus theta naught is equal to 0. This boundary condition depends on the so-called boundary phase parameter theta naught. We change from the 0 pi, and it will be only one, if you wish, random parameter in this one. But potentially of it, you have the following form. It's there are some points x1, x2, and so on and so xm, we tend to infinity, and at this point potential is high. No absolute value of the potential is high. Lattice operator is bounded, and in this case there is no difference between large positive potential or potential which is very negative, which absolute value, which negative but absolute value. I assume that I put here V1, V2, and Vn, and assume that sum of one of this value is n over n convergence, means that we have some system of the peaks which growing fast enough. And points xn are not very sparse. We will assume that xn smaller than constant to the power n for some constant c greater than. It means that they go to infinity, but not faster than genetic progression. We have such potential between points with a point 0, with point -1. I use such two points for the boundary condition. Between such peaks, everything is point. No additional assumption about potential. And theorem tells that for almost all theta naught, belongs to interval 0 pi. That this self-actuated operator has pure point spectrum. That's spectrum of H is pure point. Is pure point. No, which means that there are functions psi of x which belong to A2, which form the basis in this A2 on half axis, and they are the eigenvalues delta psi n is equal to some p sub n and psi n. And in this case, the structure of E sub n depends, of course, on our potential. For instance, if potential will grow everywhere, that in this case, will
delta or H?
no H, of course. If, of course, potential tends to infinity, is growing everywhere, that's in this case with free spectrum. But typically, for instance, in between peaks, we have some empty areas. The spectrum will be dense on the spectrum of the Laplace operator. Spectrum of Laplace operator, spectrum of delta is equal, is covers interval from -4 to 0. Because in the Fourier space, if we consider the same operator in the dual Fourier space, that operator delta will be operator delta head of k, the k belongs to false Q1, that is in the minus pi. And delta head of k, the symbol of this Fourier symbol of this operator, will be, of course, cosine k and range, and it acts as an operator of multiplication by delta head of k, and range of this factor interval -4, 0. That's if potential u of x on some interval inside between point x1 and x2 will be long enough that it will be close to 0, that spectrum will be dense. This typical situation. We have,
you mentioned almost all theta 0.
yes, this is actually an extremely important moment. Almost all. And the question is what happens for remaining theta naught, which we have measured here. But for several years, we had no answer for this question, but my student, Alexander Gordon, who died several years ago, he was relatively young, he put the following results. Here in the form. Then there exists set gamma, which belongs to this interval 0, such that this gamma is the G delta set. It means that topologically generic G delta set, but measure of gamma is 0. Because of the co-complement we have horizontal, we have pure point spectrum, and for theta naught belongs to the gamma, there is no eigenvalues at all. Spectrum is pure singular continuous. This is what Paris Simon in terminology by Simon, this is a theorem about instability of the localization. Everything is pure deterministic. There is only if you wish one random parameter. If you select theta naught randomly with uniform distribution, you get localization is produced one. On the complement, we have some particular topologically very rich set, G delta set gamma, for which there is complete del D. And what is the physical meaning? Well, this is not very good. But how to read the S, sorry.
No, it's not.
This is also not.
That C is
What?
C is not,
It's at least some sheet.
but if it's less than one,
C is greater than. You are completely right. I did growing exponentially. Excuse me, please. Okay. What is the physical meaning of this result? Assume that let's consider quantum particle, which moving in this random pattern. This is physical, it's not mathematics now. Physical consideration. If the quantum particle will be between two high potential barriers, then it will not stay forever in this interval. If potential barriers are very high, but however finite, then sooner or later, due to nailing effect, the particle will penetrate outside this block between two barriers. But in what direction it will penetrate? Now it's clear that it will move with bigger probability in the smaller, in the direction of the smaller barrier. It means that for the quantum particle, we have strong left drift if the barriers are growing. If this drift is sufficient to generate limiting distribution, some kind of, like in the zero market chains, some stationary limiting distribution, then this stationary limiting distribution will be exactly the square in quantum mechanics, the square of the corresponding eigenfunction. This is general mechanism. If we have not necessarily one-dimensional phase, in many other situations, if we have such graph, and in this graph, there are, in some sense, narrow areas where there are high potential barriers and there are high potential barriers, and these areas divide the phase space to disjoint blocks that we can expect localization. Yes, and this theology works for many classical first of all, for Sierpinski lattice, multi-dimensional Sierpinski lattice, and so on and so forth. This is, I will discuss this, but nevertheless, I will prove this theorem, or at least give some principal details of the proof. because this proof is not standard mathematical proof when he are trying to write down some integral equation for the resolvent and so on and so forth. It's everything he based on the physical idea, right? Instead of random walk, I will use some kind of Feynman integrals and so on and so forth. This is
I have a question.
Yeah.
I mean, so in your result, there is no randomness in the potential T.
yes.
So so it is purely deterministic result. It's only the boundary condition.
Yes. And this is very important. This is exactly what yesterday time was happy. No, it was all the result. Unfortunately, this result is not well published. It's why it's not very well known. It was published in our paper with Leonid Pastur and here in 90s. And, it was the time of the first Russian perturbation, first not the last perturbations, and it was published. Some small German magazine, I cannot remember exactly details, but I will give details. I will give proof of this. Yes. And proof of this here will be based on the following result by Simon and Ward. This Simon-Wolf theorem is the general theorem in the spectral theory. Assume that we have, I formulate in my one that is okay, but in general result. Assume that you have a resolvent R of x and y for our operator that is h minus e by 1. And the rule of f, this is matrix form, and assume that this resolvent, in our case, I will consider resolvent from points VR over x, and assume that resolvent is square integral for almost all energies. Very important that for almost all, because it's typically will happen on the spectrum. Resolvent will be integrable on the spectrum of operator as the set. And in this case, of course, some resolvent will be highly unbounded, but nevertheless, on the set of the full measure, we need this result. In fact, Simon-Wolf theorem, it was some generalization of the result by Catani. Catani applied a similar consideration to the case of the random, but that with independent identity distributed values of the potential, but however, ideologically, he was very close to the Simon. This is generalization, but principal ideas already existed in the Catani. But if we have such situation, and then for almost full theta naught, I consider my particular operator depending on the parameter theta naught in the boundary condition. That for almost spectrum of H, I can write down sub theta naught. This is the general theorem. And but Gardon's result, which I formulated already, that for the that there exists set gamma of G delta type of the measure zero for which there is no localization, there is no eigenvalues or eigenfunction from L2 L2. This result is also can be generalized. There is generalization of Gardon result, the called Gardon-Delaria Simon theorem. For the general, if you have more or less the result of abstract operator, which is quite integrable for almost all entities, that under appropriate rank one perturbation of this operator, we will have delocalization. All eigenstate will disappear. No, I don't want to calculate precisely this result. That's okay. It means that we must work with the result. But what is the, let's consider resolution f sub e x y. That's this resultant can be presented in far enough in the complex plane. Let us consider this resultant in the situation imagery part of E is very large. In this case, for a resultant, we can the following Feynman type representation as representation. This is the summation of all paths gamma, which connect together point X and point Y. What does it mean connect together? No, for it means simply we have something like this. If X is equal to 3, Y is equal to 7, then we can consider as a points path gamma at moment 0 is 3, at the moment 1 is equal to 2, after this again 3, 4, 3, 4, 5, 7. Any 5, 6, 7. It's usually paths like trajectory of the random walk. Each next step goes to one of the nearest two neighbors. And after this, we have product 1 over E minus Z of Z over all points Z belong to this path gamma, including initial point of this path and end point of this path. This in continuous case for the non-stationary Schrodinger operator, Feynman write down something like this. But it's impossible to understand mathematically, unfortunately. But this object, because of discreteness of the space, is very simple. So how to prove this fact? What we have the following equation. We have equation delta psi plus delta psi is equal E psi of x minus delta y of x. This is equation for the resultant. Resultant R sub E as a function of x for fixed y. Y is the singular point of my resultant. This is exactly a solution of such equation, or it can be written in the following form: psi of x plus 1 plus psi of x minus 1. Included earlier is operated at minus 2 psi of x, but I don't want to write down this term. I include this term in the potential. I can consider now that my Laplace operator is simply sum over two nearest neighbors to the point x or the psi function. No, it's divided by t minus 2 of x plus delta y of x divided by t minus d of x. This makes sense. And after this, I start to iterate. I iterate this, but of course, psi of x plus 1, psi of x minus 1 must be inside my free space on the half axis, and so on and so forth. But because imaginary part of E is very large, we have here the number of possible combination, a number of possible parts of the length n will be 2 to the power n because two nearest neighbors. But if E greater than 4 or 5, that's this formal expansion, this formal sum will converge very fast. This is representation of the result. In this representation, we have some part gamma, but it is not, I want to emphasize, it's not the trajectory of the random walk. It's simply formal sequence of the numbers. Each next number is the distance one from the previous. But in this series, it converges in very good sense, far enough, deep enough in the complex plane, we can make any operation. We can consider different groups of the such parts. We can divide parts on the several sections and so on and so forth. And it will lead us to the cluster extension of the table. What is cluster extension of this? Let us consider our point 0, point x1, when we have peak d1, point x2, when we have another peak x1. And let us call 0 block as a sequence of point 0, 1, including x1. This 0 block. But first block is between x1 and 2, including endpoint x1 and x2. It means that my block have intersection. First block contains point x1 and x2, and so on and so forth. Intersection of the two succession blocks is one point, exactly a point when we have high value of the potential. Now I want to classify, and this is again very close to the final ideas of the final diagrams. He also classified diagrams in his work about quantum electrodynamics. And let us gamma theta of K. Okay, I want to classify trajectories. I want to classify trajectory gamma, which started from 0 to some point x. There are, of course, infinitely many such trajectories, but I classify such trajectories in the following form. I introduce gamma and assume that point x belongs to the block number k. And now I consider gamma theta sub k is a sequence of the blocks between 0 block and first block. So something like this 0 block. After this, we have first block, again 0 block, third block, second block, and finally, assume that we block 3 plus 1, and after this, we equal to the block A. And what does mean V return? How to describe the dynamics between blocks if we know one particular trajectory, gamma, which goes from the point 0 in the 0 block to the point x in the block number k. The particle, this part started from point 0, it can move inside this interval 0x1. It can visit point x1 several times, but after each such visit, return to the point x1 minus 1 in the left direction. But finally, at some moment, very first moment from x1, it jumped to the point x1 plus 1. And this moment, when the first time trajectory from point x1, which may be was visited many times, jump to the point x1 plus 1, this moment is the moment of the transition from the 0 block to the first block. And secondly, for how for the first block we return back to the 0. Again, particle moves long time between x1 and x2. It's the same motion of quantum particle, which I explained at the very beginning, before tunneling. But tunneling is exactly transition from the jump from point x1. If you want to move from 0 to 1 to the point x1 plus 1.
I have a question.
Yes.
Actually about the formula of that. Probably there should be -2 in the denominator.
What?
For formula for psi x. Psi x will be.
I move v of x in the right part, delta function which was with minus, I move to the left. And divided by e minus v. What is? This is elementary algebra. This is nothing.
There's a 2.
What?
In difference, there is a 2. So in the linear probably.
Yeah.
In the definition of.
I get it. What?
Maybe it's two psi x, like it was done.
No, I think it's
What?
Depends on how you define Laplace, unhalf or without.
Yes. I said already, you lost this moment. This -2, I included in the potential.
okay.
You see, this is in such combinatorial studies, it's natural to assume that particle jump to the nearest neighbors, but not the state. It is.
Okay.
I said at some moment that in the future, I will understand data as the sum of all two nearest neighbors. Will not subtract -2 psi of x because it can be included in the potential of X.
I have also a question like so the procedure of block movement,
Yes.
is it related to somehow to renormalization?
But
In the sense that you are
I
no longer
explain you that gamma is path on the lattice Z1 plus from 0 to the point X. That I want to classify such path using information about in which order this path moves through the blocks. Because no any restriction on the path. From 0 to 1, from 1 to 0, from 0 to 1, from 1 to 2. Of course, we cannot move from 2 to 5, for instance, because of trivial elementary topology. What is extremely important here is that number of such number of the boundary points must be small. No, I can consider the situation when instead of one peak which has base 1 point, we have several such peaks. It will be in this case a bit more general, but I will formulate later on abstract version of the same. It's sufficient to understand everything in this simplest model. And for given path gamma, we can construct gamma tilde of k. This is a path on the phase space where we have only blocks. Look, we in the variant we must be in the block number k. But before it was would be k minus 1, but I'm writing here k plus 1. But length of the signals again can be argued. No, it cannot be very small. It's not smaller than k, but there is no any restriction about. But don't forget that we are still in the situation of complex energy, which imaginary part is relatively large. And because of this part, contribution of the long path will be very small. And after this, I'm writing down R sub E of with theta gamma with the index gamma theta sub k. I fix a sequence of the main blocks, and I'm writing resolving. I'm writing this expression. This is summation of the product. Not the same product as above, but summation only of the path gamma which belongs to gamma k. I fixed for path gamma sequence of the blocks in which order particle goes through the different blocks, path goes through the different blocks, and after this I consider for given fixed such sequence gamma tilde sub k, I consider summation of all elementary parts of the same product which this belongs to gamma over minus And now this path gamma, it contains several sections. First of all, it moves a long time between point 0 and x1. Maybe it visits many times point x1, but return back. But transition to this third block will be at the moment when particle will enter x1 and after it jump to the x1 plus 1. This is a transition to the first block. And so, as I explained, if we will consider summation, if we consider summation in this big sum on the different pieces of the path gamma, first of all, piece gamma which belongs to the block number 0, after this piece which corresponds to the part of the gamma which in the first block and so on and so forth, then we will find, as easy to see, the following expression, which is what I do. It's almost the cluster expansion which I want to construct. First of all, it will be R sub E. What does it mean 0 block? Okay. For any set, for any block, I can consider resolvent of the block between point 0 and point x1 minus 1. Resolvent for the block 0 for the energy between 2 points inside this block. This is the resolvent of our operator, but not on the lattice Z1 plus, but on the first final block, 0 block, with directly boundary condition. And after this, I have 1 over E minus V of x1. From point x1 minus 1, our particle decided to move to the point, to the first block. And after this, I have first block already. E from point x1 plus 1. To which point? Because we want to return from first block to the 0 block, it will be again x1 plus 1. And after this from point, it will return the same E minus G of x1. We have this resolvent describe behavior of our quantum particle inside 0 block until transition from the 0 block to the first block. During this transition, we will receive factor 1 over E minus V of x1. Maybe we have such factor earlier, because I said that we can visit x1 several times before transition to the first block. But it's not important. Let us remember that our geometric progression decreases extremely fast, and result only short trajectories have visible weight. In the moment of transition between 2 blocks, we receive small factor because V will be V of x1, V of x2, will be high peaks. And this is the cluster expansion and resolvent SME of 0 x, resolvent of our initial full operator will be summation of the resolvent R. No, because point X can be in different blocks. Yes. Gamma K. Theta. And E from, no, it has to consider summation over all gamma K theta and gamma K theta and X from 0 to X. What gamma K theta, what is written here? And after this, it necessary, because point X can be in the different block, it necessary add additional summation. This is a representation of the resolvent. We divided, we presented resolvent as some kind of cluster expansion. Each cluster corresponds to the situation of quantum particle state at the given block, main block, K in the parentheses, and in the between transition we have small factors, but a resolvent kernel, we have of course each block is finite. We have this resolvent is simply some rational function of energy E. It depends on the eigenvalues and eigenfunctions of the Laplace operator inside given block, zero block, first block, and so on and so forth. But we have no information. I said you already that we will not use any information about potential between high blocks. We must prove. And this is the central moment in this activity. We must prove that resolvent cannot be very large. Each resolvent has small denominator near a real axis. You see, we construct a resolvent only for very deep enough in the complex plane. We must extend now analytically resolvent closer and closer to the real axis, because information, spectral information, depends only on the limit of the resolvent at the point E plus I epsilon, when epsilon tends to 0. We have small factors which correspond to the high peaks separated blocks, but we have resolvents of the blocks. And for such resolvent, there is excellent estimate. We showed with Eisenman that this estimate, and it was written in our paper about localization, that this estimate belongs to Kolmogorov. I will write down this estimate. Let us use that we have summation alpha k divided by E minus E sub k, k from 1, k from 1 to n, and sum of absolute value of alpha k, it's less than equal to 1. This is lemma. This lemma, it's possible to find this lemma in one of the old papers about divergence Fourier series. And I did not know this lemma, but when I gave the talk of similar objects. Instead of this lemma, I use some much weaker inequalities, which I invented myself. But Wolf explained me that this is a Kolmogorov lemma. Let's consider such function. That's the measure. That's measure of t times z. This expression greater than empty is more or equal than 4. It's independent on the number of the eigenvalues. Block can be huge, but this lemma, which we attribute to Kolmogorov, but Alex Gordon discovered this lemma belongs to Boole, and it was published in the middle of 19th century. And the same Boole which introduced Boolean algebra, some specialists in logic. Exactly this work. I use even notation for them. But I will prove this lemma. But what is
25 minutes. Is
what?
supposed to 25 minutes. Your talk is 1.5 hours.
Okay. Okay, but I will prove now this. I simply didn't know about. Okay. I will prove now this lemma. First of all, assume that this function I will call R of t, rational function of t. I will present R of e equals R plus of e plus R minus of e, where plus corresponds to the is a part of this expansion when alpha k is positive and when alpha j is divided coefficient into groups, positive, negative, and of course this will be less helpful than measure of t for each absolute value of r plus of t greater than m plus the same expression for which r minus greater than m. And that means that it's sufficient to assume that sum of alpha k, that all of alpha k have the same sign, for instance, positive, and sum of alpha k is smaller than 1. Sum of which alpha k less than 1 and alpha next less than 1, because total sum of absolute value was less or equal than 1. But we can assume without rules of generality that all alpha k are greater than 0. Then Boole made the remarkable observation that this measure equals 4 summation alpha k over. This is ID. It's very good exercise, for the mathematical competition problem. We have the following situation. We have this sum alpha k divided by E is of k. And we have several such points for large values of B. This rational function tends to 0 and positive, but after this, I will assume that they are ordered in increasing. It's a k, it's a y, it's a n, it's a -1. But after this, okay. Thank you. And this is the label n, and this is the label minus n. I must consider in between, we have two roots when the rational function intersects with the label m and minus m. And we have here some more things. And similar intervals around next energy, next eigen values is up k minus 1 and so on and so on. And this is but sum of let's consider equation sum of iso k divided by E minus E by k minus or n minus divided. I multiply by the product of all E minus E sub k, product all denominators, and after this I will have n times E to the power 9 capital plus something else. And here I have e to the power minus 1, and here minus e to the power minus 1 times sum of e sub k. This is plus 1. This is algebraic equation. Order of this equation is n capital. N capital is the total number of the E sub k, eigenvalues. When I multiply, I will have the same equation. It follows from here that sum of the roots of this equation, but sum of the roots is exactly this such point for which I didn't introduce notation, but sum of the roots of such points due to Vieta theorem, because this can be written, I can divide it here by n. I have a algebraic equation of the order n capital. Sum of the roots is equal coefficients ahead of e to the power minus 1 with minuses. And this is exactly sum of ek, sum of ek over n. This is the summation. This is summation of such type. And I might subtract now what I must subtract now the roots of another equation. Another equation will be minus and minus. I can find some of such roots and some of such roots. The difference will be exactly what we need, and it will be exactly for alpha k over m. This is the Vieta theorem. Nothing. We must apply Vieta theorem for this algebraic equation. And Kolmogorov proof is exactly the same. I did not read the Bull paper myself, but Gadrosa means that he also used even the same notation like Kolmogorov. This is but definitely Kolmogorov never knew about this part. This is extremely important fact that that this measure is independent of the number of the points in the book. And because in the case of the fractal lattices, for instance, Sierpinski lattice, the blocks between such narrow points through a very fast, is extremely important that we have such independence. And how many time I have 15 minutes? Okay. Not very clear what to do now, because if you collect together estimations for the small denominators for the blocks and this information about increasing sequence of the V at the V sub k, value of the potential at the point xk, then after some relatively simple calculation, you can kind of listen. I will show you this is the book Random Mediates and Proof. Random media at I gave there some lectures on the random media theory in the end of 90s. And after this, these lectures were published 3 times. And this is the very last publication, because first publication included lectures of 3 lectures for given year. I was one of the lecturers, and Bakri was lecturing another topic, and Richard Gill with also statistics. But after this localization, lectures on relativism was published in Springer 3 times. This is short edition. In this case, Dan Hollander and Zeytouni did everything here about random walk as a random environment. This is Zeytouni. That's random polymers, basic condition for the random polymer by Dan Hollander and my lectures. This is the lectures random medium. There is one lecture, it's called 1 0 click. You can find here information about what I try to explain today, but I try to explain some physical motivation, but maybe I was very successful, but however, it's from my point of view, this is the most important. This is the intuition behind mathematics. You can read this theorem. I will now formulate one-dimensional result. I will formulate now general one-dimensional result because in the next lecture I will repeat everything for the general graphs. But I will have in mind mainly that this Sierpinski lattice. Okay, but the following result is the following. Assume that we have, and assume that we have blocks 0, 1, 2, and 1, 4, which have some intersections, and not necessarily one point, like it was in my lecture. But there are some intersections, delta 1, delta 2, and so on. And for each of such blocks, we can introduce R sub n of sub e of x and y. This is the resolvent for the of our Schrödinger operator inside the blocks with the zero boundary condition in the nearest two points. Declared boundary condition life, it was here. And the same situation that we have R to the power delta sub k of E again of x and y. This is a resolvent correspond to intersection of the main block. And the idea is that quantum particle cannot move, has very strong suppression of its motion inside such blocks. It's can be, for instance, it can be potential barriers. This potential barrier can be maybe lower than in the case of the single block, but if potential barrier is very wide, then it's again this potential barrier will be very strong. But assumption is that resolvent of E of delta k between what point? I need to consider only end point. In this block, there are two endpoints nearest to the endpoint of this block, because we can leave or we can enter to this block delta 2 through such 2 points. I do not write down such points, but what is very important here, the number of such points is small. It's independent on the length of delta 2, it depends only on such 2 points, because in Kolmogorov estimate for the resolvent, we have resolvent for fixed argument A and B, and measure of energies for which this resolvent is greater than m, smaller than 4 over m. This is, and let us assume that it's more or less than delta k. Sum of the delta k over k converges. This is a condition which similar to conditions that some of the height of my peaks was finite. We had conditions that should value be sub A, not be finite. And again, we assume that xn, that's xn is that point to the block. This is let's say because of constant to the power n. This is very simple. Then we have this. Then we have for almost all boundary weights we have a pure point spectrum. In the case of the bounded potential, the such blocks must be the delta. This intersection of my blocks will be very long because if energy of the quantum particle smaller than height of the potential barrier, and potential barrier is very wide, it's again tunneling has very small probability. And this is the theorem which was, I think it almost like published a long time ago. That's, I try to explain. And then now I will only say you what I will discuss. And next time I will consider cluster expansion on the general graph, and let us look on the Sierpinski lattice. I will bring you Sierpinski lattice right now because maybe not everybody has heard about this very popular object. There are many textbooks, elementary textbooks about Sierpinski lattice, Sierpinski gasket, and so on. We have the following graph that initial block of this graph is the following system of 6 points, which are formed. We have here 6 vertices, and they are connected by edges. And after this, we add empty triangle and 2 other triangles when we will repeat this construction. And after this, I consider each next triangle will be 2 times greater than previous one. And after this, this is Sierpinski lattice. It goes to infinity. And if we will compress the Sierpinski lattice and pass to the limit, in the limit you will get 2-dimensional connected counter-like set. This is the so-called Sierpinski gasket. We can consider random walk on the Sierpinski lattice. Each point has 4 nearest neighbors, except initial point which I can hold to the What is very important in Sierpinski lattice that there are points, or like 2 points which I showed. There are only 2 points that when in such 2 points we will have infinite potential barrier or very high potential barrier, then lower part of Sierpinski lattice will be disconnected with the upper part. On the line, it was I think 1 point, but here 2 points. This is so-called non-percolating graph. And what does mean non-percolating graph? In abstract sense, I will discuss later. And for such graph, for such on Sierpinski lattice point of view, introduce Laplace operator, of course, discrete Laplace operator, Schrödinger operator with random potential, and so on and so forth. But again, not necessarily, we don't need here randomness. Some localization theorem about pure point spectrum can be formulated here in deterministic language. Again, due to this effect, which I try to explain, that if potential barriers are growing, that quantum particle want to go in the direction opposite to increasing those barriers. Okay, Vasily, I want to stop here.
Okay, thank you very much.
For a fractional Laplacian, discrete Laplacian, can you do similar construction for fractional discrete Laplacian using binomial expansions of this discrete operators? It looks like
This is a very serious question. I want to tell you that there is classical Anderson model. In classical Anderson model, we have discrete Laplace operator on the way to DD, and we have random potential. This results by Veronica Spencer, and then later on the result in our later month, it shows that if potential is strong enough, it means that so-called coupling constant has very large, then in this case, the probability. This is it's true not only for lattice. It's for the 3D class of the graph, including Sierpinski lattice and any. We need only some boundness of Laplace operator. It means that number of vertices, neighbor given vertex are be bounded for instance. But you are completely right. What you have instead of Laplace operator, you consider fractional.
oh, non-local,
Yeah.
non-local, which contains.
No, instead you can consider, of course, something like this, summation. We can consider some A psi of x, summation psi of x plus v minus psi of x times A of z. It means that at the language of g is not. In this case, we can let the walk jump from point x to the point x plus z with probability A of z. And if A of z has power decay, it's exactly the what we call this fractional part. It's like stable. There are stable processes which is related to. Well, this is it's not exactly stable because this is discrete random walk, but it's very similar to stable. There is some power decay. Nothing is known.
On the spectral properties.
That's more precisely. In this modulation, you can afford if we have very small decay, that Anderson conjecture must be, it must appear as we predict. I will discuss this topic in the different sections because there is famous paper by there is hierarchical random walk by Dyson, which described, which correspond to the isothermognetic model. if one-dimensional isomagnetic model has potentially decreases flow dynamics, then it is taking the place arbitrary. That's called magnetization. And this indication that the same two must be physically very closely related.
Yes, because there is a first stable, there is a distinct stable distribution, Shibuya distribution, and they are related to the different operators, no local operators.
One-dimensional symmetric random walk. I will discuss this, but you say one-dimensional random walk will be transient if by any time we still and this is already, it's somebody appears in one dimension for degree, appears some kind of new dimension. It's well known in physics, but there is no such theory. Even if parameter alpha is close to 2, means that statistical random walk has for the moment of the order 1. It must be probably sufficient for localization, but it's not. Yeah, this is, yeah, but
We have to tell time for other figure because of you.
Yes. but on the hierarchical, nevertheless, if everything will go for the fraction, for any fraction, we always have localization, and this is the it's not always also.
Okay,
There are
so
some.
we have to postpone discussion.
Any other questions? No more questions. I have to go for lunch. Thank you very much.
Yes, I got now. Yeah. But we're going, so it's for lunch.